Hello everybody, Raúl here from Palo Alto, California, presenting in this PhD doctoral meetings my progress in this hydrogen fuel aircraft configuration and trajectory optimization to reduce aeronautic environmental impact, the title of my thesis, supervised by Manuel Soler and Raúl Cavallaro. So as you may know, hydrogen has emerged as a promising long-term sustainable solution for aviation, where direct carbon dioxide emissions are eliminated, and it can be produced by renewable sources. On the other hand, hydrogen aviation could also contribute more to non-CO2 emissions in terms of water vapor and contrails that it has been recently demonstrated that can play equal or even larger noxious role to the environment. Luckily, the mitigation of these non-CO2 effects has been promising through operational strategies like trajectory optimization or rerouting. This is why we decided this twofold approach for this thesis, tackling both the research and design of the hydrogen aircraft conceptual models as well as its operational and trajectory studies. So rounding off the problem and tackling both carbon dioxide and non-carbon dioxide emission impacts. We can divide this thesis in three blocks, starting from this hydrogen aircraft design optimization, where we use models in order to try to optimize its configuration and design. As a second block, we have the emissions and also the atmosphere in terms of weather conditions that are both crucial inputs and effects that has to be estimated for this rerouting using in-house libraries as Rock and Roost able to do trajectory optimization. This is why we determine as objective of this thesis to analyze the introduction of the hydrogen aircraft, quantifying its climate impact reduction potential and derived cost, and as minor objectives to develop hydrogen aircraft design analysis and optimization models to be able to estimate its emissions and to model its climate impact, and also to obviously develop climate optimal trajectory planning algorithms for this aircraft. So firstly, in aircraft design optimization, what we need are digital tools to predict the potentials of this hydrogen technology, since we don't have previous knowledge and we don't know the best design practices for this kind of aircraft. That's why we introduce here the design analysis and optimization, enabling the automated search for the best aircraft candidates at early phase of design, so incorporating a physics-based decision making into this design phase and transforming this into a numerical or mathematical problem to be optimized. For that, we use our in-house tool, in-house library called Motivation, built on top of OpenMDAO, that uses gradient-based optimization for estimating, for predicting these hydrogen aircraft capabilities as well as its emissions and cost. So basically what we are doing in the core of this tool is to make this candidate, this aircraft, fly on a mission where at each point we try to solve this balance of forces equation, iterating the throttle, in this case of the turbofans, and also estimating at each time its weight, so solving the equation, as well as we incorporate the new tailored components for the hydrogen aircraft, as it could be the new turbofan or the cryogenic tank storage liquid hydrogen. Among the improvements and enhancements done in this platform, we have the mission module, where we compute the takeoff and landing maneuvers, as well as we estimate the aircraft capabilities for fulfilling these minimum climb angles after taking off and before a rejected landing that are needed for its certification, as well as this holding segment. We use semi-empirical relations from different sources for estimating the weight and the aerodynamics of this aircraft, modified in order to incorporate the hydrogen powertrain. And we also incorporate the surrogate model for the turbofan, basically from data extracted from a dedicated pool called Bicycle, where we can estimate the thrust, fuel flow, fuel to air ratio, and inside engine parameters from each flight condition based on Mach altitude and the throttle input. For calculating the cost on these emissions along the mission, we can directly have the emission index for carbon dioxide and water vapor directly from stoichiometric values. It's a bit more complicated for NOx emissions. So we incorporated here generic correlation models that all rely in this form. So rely on basically the conditions in the combustion chamber, temperature and pressure. So for preliminary results, we launch here an optimization campaign where we compare the A320neo versus an optimized A320 retrofitted with hydrogen. What we do here is change the conventional turbofans for ones run on hydrogen. And also we enable the possibility of stretching the fuselage for allocating the cryogenic tank to the rear part. So computing the remaining space in cabin in order to estimate the maximum payload that we can carry. The objective function for this optimization is basically the fuel consumption during the nominal trip. In one case, it would be kerosene. In another one, would be hydrogen. Obviously, the changes applied to this aircraft would affect its weight and drag. So we compare here the increment from conventional to the hydrogen aircraft in this payload range diagram. Where, as we can see, we can achieve nearly 100% reduction in basically carbon dioxide emission. It's not 100 because we also consider the emitted carbon dioxide during the hydrogen formation. And also with the correlation models incorporated, we also achieve a 55% reduction in NOx emissions. On the other hand, we have more than double of the cost and the water vapor emitted due to basically the high cost for producing hydrogen and its stoichiometric relation for emitting water when it is burned. So as anticipated before, the next question that arises is what do we do with all this amount of water vapor? So that can be noxious for the environment and also can trigger the formation of contrails. So for that, we need to study the aircraft operational and trajectory optimization. So being able to identify these sensible areas more damaging to the environment. How we do that? This is a problem because contrail formation and its effects is still very uncertain, and the hydrogen aviation is a case not really addressed at all, and we have no information. So current tools used cannot be used. So for that, we have identified as a solution the use of high fidelity simulations that can capture very well the control physics and can set up experiments in a very controlled environment. The challenge that arise here are basically the validation of this platform and to derive cheap products that can be used later for trajectory optimization, as well as the augmentation of these simulations to hydrogen mixtures. From these challenges, it has emerged this collaboration project that I'm developing right now at Stanford University, where we want to use the images from ground cameras of contrails, where we can measure its properties as well as estimating the environment and basically the atmosphere where they were formed, in order to replicate these conditions into a CFD solver called Charles, where we simulate, where this group at Stanford are simulating the control formation and its development. We want to compare both results in order to identify trends and in order to enhance our knowledge in control formation, with the eventual goal of deriving cheaper products for estimating the control and its impact for trajectory optimization, as well as extrapolating these models for sustainable aviation fuel and obviously hydrogen. So we aim at this project to build a control dataset where we can collect information for each individual, as well as its properties, also the aircraft and the conditions where it was formed. So being able to compare these different trends, these different condition against the simulator, and also being able to compare the evolution in both cases using probably more qualitative than quantitative values as maximum, minimums, and whichever we can measure. So we expect here to identify the threats, the risk, and the reliability of this methodology, as well as trying in the best case to search these trends and to enhance our knowledge in control formation, for finally trying to make some product applicable for rerouting and for trade optimization. Finally, talking about my next steps, I am now under this research stay at Stanford. I have also a journal paper sent. This paper is about the feasibility studies on regional aircraft with hybrid electric powertrains, done also in the aircraft design optimization platform. Regarding also hydrogen aircraft design, I am under developments of improvements in terms of new configurations, as it could be the double tank, as well as improvements in the study of the longitudinal stability of this aircraft, improvements in the drag model estimations, and with the aim of realizing a complete optimization campaign in order to write another journal paper. The result from the circular design will be obviously needed to be encapsulated into a dynamical model for using the in-house libraries of trade optimization and to optimize these routes in order to compare the costs and the climate impact against the conventional aircraft. Finally, I leave you here in this slide basically my contact, my supervisor's contact, as well as my achievements so far during the PhD in the form of research stay, papers, conference, and scholarship. Thank you very much for watching this presentation, and see you soon.